So this is just to get us going in the morning. I don't know if any of you have ever sailed, but capsizing, I guess, is a risk you take, not particularly a dangerous one. It relates to many of the things that we have begun to talk about. Clearly, as you go down in the water, you'd feel the pressure increase in a liquid, and we know exactly how that occurs. When you pull on the centerboard to be able to right it, you're pushing against the motion of the sail. So it's a little bit different from what we're talking about in terms of our behavior with just a static pressure, because it's actually the resistance to motion that you're pulling against, but you're putting a moment, a torque on the boat to be able to pull it up. And so if you might have looked at some of the stuff we talked about for 3.1, you'd have seen some of the aspects of that in terms of how we deal with forces on structures. And so this is just kind of an appetizer to get us going in the morning. The other thing that I might do, I'll pause this, is instead of doing our usual recap, is actually do a real recap and just play this at multiple speed. And so it shouldn't, I think I've killed the sound on it, hopefully. And so this was the stuff from 3.1, talking about the comet. Comet was a plane that kept on dropping out of the sky in the 1950s because of fatigue cracking and square windows were the two causes of this. And so the various things that you saw were the comet, the inflation multiple times as you pressurize and depressurize as you take off and land. These planes just didn't return. They didn't come into their destination. They disappeared on their flight, and they figured out that two things. Square windows, which you never see now in planes, act as stress concentrators, and also the fact that the fatigue cracking from pressurizing the cabin and depressurizing it multiple times grew cracks that ultimately destroyed the fuselage, and they broke up in flight. The second one was this Aloha Airlines, which ran sorties between the islands of Hawaii, and so would make multiple runs in a day, short flights, 20-minute flights, so you can imagine how many runs you get. And the roof peeled back on one flight. I believe a flight attendant, unfortunately, was sucked out, but it actually made it back to base without any real problem. And, of course, the dam buster stuff here, which perhaps is not so relevant because it's not talking about fluid pressures on structures per se. And then this was, well, I guess the relevance for this is that, if you want to destroy a dam, you don't hit it with a bomb on the surface because there's no confinement. You have a bomb that runs its way down the reservoir, drops down at the base of the dam, behind the dam, and therefore the pressure of confinement is what allows it to have some impact when it explodes. It confines the explosion and makes it much more destructive than it would be otherwise. So this is what was used in 1940s against German Nazi dams, I guess, at the time, to be able to destroy them. So that was kind of the preamble in talking about fluid pressures in all of this. And what we'll do today is we'll recap the stuff that was in this, but the basic idea is that if we know pressures at a point, we can also calculate what pressures would be on structures. And the structures might be, for instance, the fuselages of a plane, to be able to figure out exactly, in this case, what the stresses are that are applied on the fuselage, and how thick the aluminum might have to be able to withstand that pressure, 2.5 millimeters. And there's relatively straightforward calculations that we could do to be able to make that calculation. Most of our interests are for fluid pressures applied in liquids. It's very easy for gases because the pressures are basically uniform. But in liquids, we know that the pressures vary linearly with depth. And so there are three things that we have to know. We have to know the resultant force, which is F sub r. And we have to know where it acts. And to calculate where it acts, we use moments to be able to evaluate that in the same way that in writing a sailboat, we might use moments. And once we know where it acts and what the magnitude is, we can use that in some useful way to make some distinctions of whether a structure will fail by presuming a particular deformation mode. And so those are the three things that we'd like to be able to do, and we'll repeat today. How do we calculate what the magnitude of this overall resultant force is? How do we figure out where it acts? And we do that by taking moments. And then once we have that, how do we use that usefully to be able to say whether a structure fails or stays in place? And so that's where we're going with this. And so that was a rapid review of exactly what you should have looked at maybe in the last few days. You have, if you're going to do the video and the quiz, you have till Friday at midnight to do it. So a Monday class, even though it was a holiday, 2 periods later, at midnight on the Friday, the things will close. One on a Wednesday would close the following Monday, etc. So there. So that's where we are. Fluids in the news. Well, apparently the strongest storm ever recorded in the Atlantic, Hurricane Irma, is gearing up. It's moving through the Leeward Islands right now, and up through Puerto Rico probably as we speak, and then up into Florida over the weekend. And so, yeah, so clearly fluid mechanics, right on the heels of Harvey, of course, as we know. And so we won't necessarily dwell on that. And I guess what else is in the news today? Well, North Korea still. This might seem irrelevant also compared to fluid mechanics, but talking about landslides, we've talked about accelerations in fluids. Of course, the mechanism by which landslides occur is that you give an acceleration horizontally, so that instead of the weight just going down through the vertical vector on like a beer can or a can on an inclined plane, if you give a can on an inclined plane the plane a shove, the can will tend to move down. And the reason is that you're basically giving the can an acceleration that's horizontal that does two things. It gives you a down slope component of the force, which increases its desire to move down slope, and it also gives you, normal to the slope, a reduction in stress, and therefore reduces the frictional strength. So it acts in two different ways. And so it's no great surprise that if you have something that's probably down a few hundred meters that gives you a magnitude 6.3 equivalent earthquake from a thermonuclear device, rather than a hydrogen bomb in this, apparently a hydrogen bomb, is that it gives a big shake to that because you can feel it many hundreds of kilometers away, and not surprising that hill slopes in a very mountainous country like the Korean Peninsula, which are kind of metastable anyway, ultimately fail. So that's kind of also related to some of the things that we're talking about in this class. Okay, so I'll leave it at that. All right, what else? That's probably it. So let me get back into this. So this is where we're going today, I think. So this is our plan for today. So we're talking about fluid pressures and how they're distributed below the surface. And as we mentioned before, it only matters when they're in liquids because it's a very simple problem to solve when it's in solids. So let's go off script and do something off script. Just because we can. And so today we're in week 3. It's the Wednesday of week 3. And so today we'll assign groups for the presentation. We said the Wednesday of the 3rd week, which is where we are. And so this is pressures on structures. And the idea is relatively straightforward. And it revolves around some things we've already done. And that is, if we look at, for instance, the pressures that result from having a distribution of fluids, where we know that the pressure is equal to the unit weight times, let's call it Y in this case. I know we've been calling it Z in the past. There is a reason why we'd like to call it Y now. And we will do throughout this session. We mentioned the idea that we had a right-handed coordinate system, X, Y, and Z was positive upwards. But let's abandon that just for now. What we'd like to be able to do is we know that this fluid pressure distribution, as we go down with depth, gives us a magnitude. I guess I could have drawn the arrows the other way. But it gives us an overall magnitude which we'd like to be able to calculate. And we'll call that the resultant force from this location, I guess y equals 0 at the top. And this location, y equals, let's call it yb at the bottom, for the base of the distribution. And so this is acting, if you like, on a structure which is here. If I try and draw it in perspective, it would look something like this. That's between those points. And we want to know what the force is that's acting in this direction. This is our resultant. So uppercase R is for resultant. So we can do that pretty straightforwardly, merely by writing that the force that we get is going to be equal to the pressure at a point multiplied by the area. And this area, if we were to draw this out, maybe I'll draw it this way. This is some width W. So this is equal to a pressure times an area, which is a width times a little differential length. So some differential length along here is just what we'll call d sub y, or dy, not d sub y. And we also know that this pressure is given by this magnitude here. And so if you write this out in longhand, the pressure is equal to the unit weight multiplied by its distance, multiplied by the width, and multiplied by y. The integral is between y equals 0 and y equals yb. And if we just do that simple integral, noting the fact that the unit weight and the width and that's it, falls out of the integral, y dy is equal to a half gamma w y squared evaluated between 0 and yb. And so if we do the calculation for what that is, we find out that it is equal to the unit weight, this term here. It's equal to the width times y times half y. So I'm just writing this out. And if we substitute this limit, then this is actually yb, and this is yb as well. And the reason for writing it this way is that you see that this term here is equal to the area of this plate. So in other words, it's equal to a width of W and a depth of YB. So this is the area of that plate. And this other term, a half YB, for the case where the plate actually intersects the surface, is we could, well, actually do two things. Well, no, I don't do that. So if you look at drawing this, this is the center of this plate. And this magnitude is YB, a half YB. And so this term here is actually called, we'll call it HC. And HC is just equal to the depth of the centroid. Of the plate. So the depth of the centroid of the plate is the balance point for that plate. If you take that blue plate that was outlined in blue, and you take it just as a sheet of paper, and you try and balance it on your finger, then the place that it would balance around is the centroid, which is this green spot right here. It would balance in both directions, but we're really interested in the depth of it. And so we can always get the magnitude of the force that's acting if we use this expression. It always works. And so we'll write this expression as the force, resultant force, acting on a flat plate is always the unit weight of the fluid it sits in, the area of that plate multiplied by the depth of the centroid, H sub c. Same terminology that's used in the book. And so if we know that, we can always calculate the magnitude of that force. If we wanted to rationalize why that is true, maybe it's worthwhile doing that, is if you, for instance, draw the same figure we have at the top again. I'm just going to do this. And let's now, instead of assuming that the plate is where it was, let's assume it starts at, we'll call it Y top and Y base. So now the plate is going to be, if I draw it to perspective here, so this is the plate that we want to be able to figure out what the pressure is. So if we wanted to do that, then we know that the pressures that are acting on it would be given by this portion of the pressure distribution diagram, right? We can draw arrows across here. And so we know that the magnitude of this resultant force, which we know is just the integral of this green area underneath the curve, we can just by inspection, immediately we can see that it's going to be given by a point that does this. So if I go halfway across here and halfway across here, so this here, actually I don't want to do that. This point here is halfway down the plate, right? So this is halfway down the plate. And hopefully you can see that if you take this little triangle here and place it here, then they exactly match each other. So if we subtract it from here, I do a minus sign, and we add it to here, then this is exactly the pressure distribution we end up at. And so you should be able to see that if this is pressure, I didn't label this, and this is depth, then this is exactly this expression. The resultant force is equal to the unit weight. The area is going to be this height here multiplied by this width here. What should I call this? Let's call it delta y in this case, right? So this area on our diagram is delta y multiplied by w, this area. And the reason that we multiply by the depth of the centroid is that this is the centroid of this plate. And so this particular height here, below the surface, and this is the surface of the water, obviously, because the pressure here is 0. This is the depth of the centroid. And so it's useful to draw it out like that because this is always true. If we know where the depth of the centroid of a structure is, it doesn't necessarily have to be in the middle of it. Different structures with different flat planes would have different locations of centroids. But this is always true. And this is always, importantly, this is always the vertical depth, which I guess depth means. Below surface of the fluid, I guess. Right? So that's the first point. So that's important to understand that. So that's the physical reason why this is true. Basically what this is saying is that the average force that acts on this plate acts at the centroid, and the magnitude of that average force is equal to the unit weight times the height. So actually that's right. So HC times unit weight is equal to the average pressure on that plate. And if you multiply that average pressure by the area, that gives you the area. That's exactly what this construction says. Okay? So it's important to understand that. So that's the first of our 3 points that we said. We said we want to figure out what the resultant is. We know how to do that now. If we know what the resultant is, we want to know where it acts, which is not at the centroid. So note that down, put that in your mind, but we'll figure out where that is. And if we know the magnitude of the force and the location where it acts, we can do something to be able to say something about how a structure might fail. So the second part then.
I have a question.
Yeah.
Can you explain why the force is acting on the center of that square instead of a little lower, since you have a skewed pressure distribution?
It's not skewed.
I mean,
it's linear.
Well, yeah, it starts low at the top and then it increases. So the moment that would cause would be the same.
We're not resolving moments. If we were resolving moments, you'd be right. But we're resolving now just forces. And so this, by similar triangles, this has to be exactly the same as this.
Yeah.
We will resolve moments now.
Right.
Okay? Right. You're ahead of yourself, ahead of us. Okay? Everyone else okay? All right. So we'd like to know now, we'd like to know what the magnitude of YR is, where it acts. This force does not act at the centroid. So remove that from your mind. So what we can do, I suppose, and I don't know whether, yeah, let's just do it. That's why I used this diagram before. Let's go back to this, this other diagram. So this might be easier. So it's not important that you know how to derive these things, but it's probably useful to be able to understand where these things come from. So I've made 3 things. The first one we've done is this. The second one, well, we're not going to worry about because you know how to resolve forces. The second thing is where do they act? And that's what we'd like to figure out. And we'll find out that the location where the resultant acts is given by this expression. And we'll explore exactly how we get that. And so one way to do that is basically to make the same construct that we've just done. And so what we've done now is we've done this. This is the little exercise we've gone through. We've said the resultant force is equal to the integral of the pressure over the area. We've substituted for the fact that the pressure is equal to unit weight times distance below the surface. And we come up with an expression which gives us basically this. What we could do is if we have this diagram, which is the pressure distribution, we know that the resultant force acts somewhere in this diagram, but we don't know where. We're going to say that when the plate intersects the surface, that the depth below that surface is YR. And what we're going to do is we're going to take moments about that particular point. We could take moments about any point we want, but we're going to choose this point where it intersects the surface. And so basically from this, we know, just from statics, the moment around R is equal to the lever arm multiplied by the force, by definition. So Fr is trying to move it counterclockwise. Mr is trying to restore it clockwise. So they balance. So if we can write this expression, then we have this. So that's the calculation we're going to do. We can do it in two ways. We could do it differentially, which is what we'll do now, or we could do it with kind of block diagrams of these pressure distributions, which is another way we can do it. But there are two different ways we can do it, but they're the same thing. So if we go to the right-hand side of this, this is exactly that expression. This is what we want to know. So we can rearrange this expression in this way. And so if we want to get this, and we already know that we can get this, then so long as we can figure out what the moment is, then we're home and dry. And so let's figure out what the moment is. The moment is exactly the same calculation as the force. The only thing that's different is that in this integration, we have a lever arm which this acts through, which is y. So if you like, this little force that's acting here, the force is equal to P times the area over which it acts, but the moment is equal to P times the area over which it acts multiplied by a lever arm. So the difference between the force that acts and the moment that acts is just this y. And so if we go through the same linkages as before, substituting a magnitude of pressure, we end up with an expression which is an integral again. Instead of having an integral of y, remember before we did this, and we ended up with a half y squared. Here we have y squared dy, which you know is going to be something like a third y cubed. So we can do that. But the only point of making that is zooming out again to the big picture. And the big picture is you want to know what the moment is to be able to calculate this lever arm. We've summed up all the small lever arms that go into this, but we want to know the resultant one because that's much easier to do our calculations. And so all we need to do is take this value of F sub r, take this value of the moment, the resultant force and the moment, substitute them into this expression, and I've just put them in here. They also have the unit weight that they're multiplied by, but I've just dropped that out because that exists in both. And we end up with an expression like this. Looks kind of complicated, but it's certainly something that you will have seen in your mechanics classes, I guess 211, physics 211. And what this is this is a second moment of area about an axis, and this is the 0th moment of area about an axis in their terminology. Doesn't really matter what they are, it's a standard result. And the bottom line is we can write this expression as the location where the resultant acts as a function of this term, the second moment of area about the x-axis, and divide it through by what is this integral? The integral y times w is going to give you an area, right? And this remaining y that we have here is going to give you a lever length. So the units of this is an area, and this is a lever length. And it's the location of the centroid of the plate. Sometimes it's not always convenient to be able to write the second moment of area about the surface, but it's easier to write it about the centroid of the plate because we know where the centroid of that plate is. And so this is another standard result that allows you to write this, and this is the only one that we'll use, is that this is the second moment of area around the x-axis relative to the centroid. That's what these terms are. And this is the y-coordinate of the centroid and the area. So you don't need to do these integrations. You need to take this final expression on trust. but we've derived it at some stage. But this is basically where it comes from. It comes from just summing moments against forces and lever arms. So it's not magic in any stretch of the imagination. So the important things are that now we can calculate for any plane that we have, and this is a plane that is completely submerged. The coordinate system that we use is this coordinate system with y down into the water and x along the surface of the water. So this x-axis is along the surface of the water. But importantly, this y-axis can be inclined. It doesn't have to be vertically down. We said before when we calculate the depth of the centroid, h sub c, that is definitely the depth below the surface, the vertical depth of the centroid of the plate. But even if the inclined plate, that's true. But this is definitely yc that we use here. And yc is the distance from where the x-axis is on the surface of the water to the centroid, but in the plane of that plate, not the vertical one. So the centroid is here. The plane is below the surface. So the water surface is up here. The plane is below. The centroid of the plane is in the middle, which is where this X marks the spot here. And there are two things we need. We want to calculate the resultant force, which is equal to unit weight, the area of that plate, and the depth of the centroid, h sub c. And we want to calculate the lever arm, which is equal to, I'm just going to write this out, a standard result for the second moment of area relative to the x-axis and through the centroid, plus the area of that plate multiplied by the y-coordinate of the centroid, squared, divided by the area and the y-coordinate of the centroid. Okay. So those are the two standard results you need to know. Importantly, and I'll reiterate this, this YC is in the plane of the plate, and it turns up here and here, and it very definitely is different from this, which is a depth. Yeah, go ahead.
So, for this case, is that HC equal to YC?
No, it's a perspective drawing. I don't know if you can understand my drawing. My drawing is the surface of the fluid here, a plate that's inclined. The intersection of the axis on the surface is somewhere up here. And so my thumb is x-axis. My first finger is the y-axis. The y-axis is in the plane of the paper. You see the perspective in that figure?
So the y-axis is in the plane of the paper.
Yes.
But,
No, the y-axis is in the plane of that plate, which was the paper. Okay?
So actually there are two coordinations.
No?
There's one in the plate plane, and one is in x and y.
There is only one coordinate system here that's drawn. The coordinate system...
Is the distance.
Yeah, yes, that's not a coordinate system. That's just...
To the surface of the
Yes. So if you're sitting down here, sitting on this plate, you look above you, that's the distance to the surface that you have to swim up to get to the surface. This is in the plane. Okay? All right. So this doesn't really show it. This x-axis is actually on the surface, right? So it's just the perspective. It's coming out of it. Right? All right. So these are absolutely points 1 and 2 that you need. And it's important to make those distinctions. I guess the other point I'll make, which probably is not important right now, is that so now, once you have those forces, we could choose anywhere to take the moments to be able to get equilibrium. Anywhere. But if you're looking at a mechanism by which something fails, then you have to take the moments appropriate to some failure mechanism. And so we'll get to that in a moment. Right? So, let's do an example. So this is an example of a plate. Happens to be in the vertical direction. I guess what I didn't mention, and I should have done, is that these results for moments of areas and moments of inertia are standard results that you'd have seen. So for a plate, the value of this term that we've been talking about is just this magnitude here, where this is just the depth A, this is the depth B. I'm sure you'll have seen these results in your statics classes, and etc. So they're standard results for this. And physically what it means is that this is the moment of inertia about the x-axis, which is horizontal, and relative to the point which is the centroid, which is the center of this plate, the balance point. Not the surface. We've just transformed it from the surface, which is y equals 0, to the center of the plate, just because it's easier. Likewise, there's one for a circle, which is this, which we'll use. Yes?
So, in like each term, physically is the moment of inertia, like how likely it is to, or like resistance to being able to spin it around that point, or rotate around that point?
Yes.
Similar to like mass.
Yeah, well, it would be for mass if it was dynamic, but here it's the pressures. So it's the propensity for those pressures to rotate it around that point. Yeah. Which is really what we're calculating, right? A net force relative to that point. Okay. Let's go back to our example. So this is the idea that we have a plate below the surface. And the reason that we might think about this could be a valve, like a butterfly valve in a carburetor, if any of you know what a carburetor is, now that we have fuel injection. So imagine a plate that has a central spindle through it and can rotate. And so this central spindle sits here, and there's pressures working on either side. And what we could imagine is that if we draw this pressure down on this side, so there's no water on here, what force do we have to apply to this point to keep it closed? Or should it be this point or this point that we keep closed? So that's the question that we might want to address. And so our solution is this. What is the magnitude of the force that's acting on that particular location? Well, the force is equal to the area of the circle multiplied by unit weight times the depth of the centroid. I suppose we could go to the expressions that we have that define the centroid. We'll come back to that, don't worry. Just to make sure that we know this. The balance point, of course, for a saucer is the center point. You can imagine putting it on your finger. The moment of inertia is given by this, pi r squared over 4. And of course, the area of a circle is pi r squared. So this is the term that we're going to use. This is just the moment around the y-axis, which we would rarely use, but we might do. Okay, so let's go back to our calculation. I should make it smaller so it fits on the page, right? So we know the centroid is the middle of this plate. So that's it. So in other words, this would be what? This would be h sub c. In this case, also, y sub c is equal to that. Only in this case, just because it's vertical, right? Our two axes are coincident. If we want to calculate the location where the resultant force acts, we use this expression that we had before. This is just written a different way, right? This is the first moment of inertia, first moment of area about the axis, which is, so this term here is pi r to the 4 over 4. This term here is yc, which is equal to 10 meters. And the area of the circle is pi r squared. And again, the depth below the surface is given by 10 meters. If you substitute those in and do the math, then you end up with this calculation. I won't go through it. You can do it just as easily as I can. But you end up with a depth which is 10.62 meters. It actually comes out to be 10 meters, which is, of course, the depth of the centroid, plus some small adjustment. The small adjustment is due to the fact that the pressure distribution increases as you go down. And so, for instance, if we drew, let me actually draw it here. If we had the plate acting at this location here, and this is the surface of the water, we know that the pressure distribution as we go down through this plate has to equal something that looks like this. We know the middle point of this would be here, and this particular triangle here, and this particular triangle here would be the inverse of each other. So that's why this value HC allows us to calculate the force that's acting. But importantly, the location where that force acts, this is the centroid. The location where this force acts, which we haven't calculated yet, F sub r, is equal to this distance YC, which is this, plus 25 over 40. So this distance here is 25 over 40, which is, I guess, 0.62. And that makes sense because we're taking lever arms relative to some point, and a lever arm with a big number as you go deeper, the question we had earlier, gives you a larger effect. So the location of the resultant should always be below the centroid. If you get something that is shallower than the centroid, then there's something wrong. So this number should always be larger than centroid. Yeah?
The question I have is, in the equation that you made us write on paper, is I over A YC, but why in that one we have plus YC again?
Oh, it's just rewriting it, right? So you could also write this as if you can rewrite this equation here, which is IXC over AYC, and we can just split it up as AYC squared over AYC. It's just manipulation. So it's just a different way of writing it. So I probably should have used the same equation, but the reason for writing it this way is it gives you a physical description of the fact that it acts through the centroid plus some small amount. And it's always going to be below the centroid of that plate. And I won't confuse you by talking about... actually, well, he says he won't confuse you. The location that this acts is actually the centroid of this pressure distribution. So in the same way that we talked about this being the centroid of a plate that you balance, if you folded this up to get the pressure distribution, so this is the pressure distribution that's acting on this plate, and if you took origami, right? If you balanced this around my finger, you'd find that the balance point would be 2/3 of the way down here and 1/3 of the way up here. That's exactly the location on a square plane that this would act. And so that's a standard result. So the idea of the centroid for the plate being the plates is the balance point of the plate where we calculate where the location y sub c is. Oops, where is it? This magnitude here. The actual location where this acts is the pressure distribution, the moment of area, the centroid of the pressure distribution, which is 2/3 of the way down from the peak and 1/3 of the way up, if it was intersecting the surface. But maybe we don't want to go there. All right? So the other thing we could do is we talked about the location where it acts, and in this particular case, it's only significant where it acts vertically. You could also do it to figure out where it acted horizontally, and the standard result for where it acts horizontally is this expression here. This is the first moment of area for depth distribution with y around, depth distribution with y relative to the x-axis for the centroid. And these are just the same terms as before. This is the location of the centroid. So if you put that into this particular case, this term for a circle, if we go down, should be 0. And if you put that into this expression here, then this is 0. So, and this is the centroid. So the other place where it acts says that in the middle of this circle, the place where the force acts is not only at this point, which is 10.62 meters below the surface, 0.62 meters below the centroid, but it also acts at this point on the center line. That's the x-coordinate where it acts. So we have both the location of the resultant vertically, which is usually the most important one, the location horizontally, and we didn't do the calculation for the force, but we know that this is equal to 10 meters. We know the area is pi r squared, and we know the unit weight of water. And so that's it. So those are the first of the two things that we said, right? We said we like to calculate, one, the magnitude of the resultant force. Two, we'd like to calculate the magnitude, location where it acts. Typically the y coordinate where it acts. And to do that, again I'll repeat myself, we use the depth below the surface of the centroid of the plate and the y coordinate of the centroid of the plate relative to the surface. Those are two distinct things. Those allowed us to calculate those two things. But what they don't allow us to say is whether the structure will fail. That's number 3. And so the final one to do is to use the information we now have to be able to figure out whether this butterfly valve will open. And so what we know now, we have a magnitude of the force, we have a location where it acts, and so we can draw this figure here. We know that the force acts here, and we know the magnitude. The question now is, if we draw down the water on this side of the structure, so there's no water here, so there's only the force, the resultant force that's acting, how do we keep this gate from opening? Well, the one way to do it is to provide a force here, which I guess I'll call F shut, F sub S. And we want to be able to calculate that. So we made the point that the way that we could calculate where the resultant was done by basically taking moments around any point within the structure. F times y is equal to moment. And we can choose the moment around any point. But if we're looking at failure of this particular valve, then the moments we have to take are the ones that say something about its failure mode. And the failure mode would be rotation around this particular point here. And so we can just do the calculation. And the calculation is going to be equal to FR times LX equals Fs times Ls, right? The diameter of this plate was what? I didn't even look. Is it 5 meters? Sorry, radius was 5. So in these, this is going to be 5 meters. This, we don't know. The resultant is going to be 7,700 kilonewtons. And the lever arm relative to this is going to be 0.62 meters, or 25 over 40 meters, if you prefer fractions.
Can you explain what LX and LS are?
The lever arms. Sorry, yeah. So we're taking moments around here. I guess I could draw them on here. That's probably better, yeah. Thank you. So this is Lx. Is it diameter 5 or radius? Yeah, I think it's radius, yeah. Yeah, I say all kinds of things, but I'm usually wrong. Don't pay any attention to me. That's it. So again, 3 points. 1, resultant force, we can calculate the depth of the centroid of the plate below the surface is h sub c. That's what we use. 2, the resultant. The dimension we use in that is the linear dimension from the surface to the centroid in the plane of the plate, y sub c. That allows us to calculate the location where that force acts. And with those 2 pieces of information, we have enough to be able to calculate a failure mode, if you like, in this particular case. And so the rest of the calculations are here. You see it down at the bottom. The magnitude of the force apparently we have to apply is equal to this. Okay. So don't worry. Yeah. So you can see this. Another example. I mean, we have 2 minutes. I don't know if it's worth any questions. I guess maybe I'll take questions rather than go through this.
For the resolution of the x coordinate of the resultant force, what was the moment of inertia?
The moment of inertia is, in this particular case, it's this. And the reason for these 2 distinctions are that the fluid pressure is varying with y as you go in the y direction, but you're taking the moment around the we're taking the moment around, I guess, the y direction, and so it's not around the surface. And so the moment of inertia for this particular case was the one we looked at, which is 0. If you can see that, which just means that because it's symmetric in this plane, you'd think that there's the same moment putting on the right-hand side of the plate as there is on the left-hand side of the plate. So they bounce. So in terms of sense, that makes the case. Also, in the case of a plate, this moment of inertia is just equal to 0, which is again saying that it's symmetric. There's the same force acting on one side or the other, and so it doesn't twist.
Hey,
Welcome.
why do you think the center, the centroid is the failure point for that example?
Because didn't have to. Because that's usually because a valve like that would fit both ways, I guess, be symmetric. No other reason. It could be anywhere. It could be the top, for instance, hinged at the top, and you could look at where you'd put other forces.